All right. Good afternoon, everybody. Welcome back to our Growing Inside the Box webinar series. Today we'll be discussing micronutrient management in hydroponic systems. So as with many of our other webinars, I've broken today's topic into two sections. In the first section, we'll be discussing micronutrient deficiencies in depth, looking at what micronutrients are, the differences between mobile and immobile nutrients, and the visual symptoms of deficiencies and toxicities. In the second section, we'll touch on potential sources for micronutrients and how to manage them in your hydroponic systems. So let's go ahead and get started with micronutrient deficiencies. Micronutrients are needed by plants in much smaller quantities than macronutrients. However, just because they aren't needed in larger quantities, each micronutrient does play a crucial role within the life cycle of the plant. Plants cannot complete their life cycles without each and every nutrient. There are several micronutrients, including boron, iron, manganese, copper, zinc, and molybdenum. Chlorine has also been identified as a plant essential element, so we will also be discussing its role in plant health today. So because micronutrients are needed by plants in such small quantities, they're usually measured in parts per million rather than in percent. Usually in nutrient solutions and plant tissue tests, we'll test macronutrients in percent. Micronutrients will be measured in parts per million. Like macronutrients, the availability of micronutrients is heavily dependent on the pH of the root zone environment. This is true for all growing systems, including traditional field soil, soilless growing media, and true hydroponic systems. Now let's take a look at the individual micronutrients and their role in plants' life cycles. Iron is the first. It's required by plants for the synthesis of chlorophyll, and it's a crucial component in electron transport pathways. In nutrient solutions, iron is typically supplied in chelated forms, which allows for increased solubility across a broader pH range. These chelated forms include EDTA, DTPA, and EDDHA. In our formulas, we use all three chelated forms for maximum solubility. Boron is also required by plants. It's needed for meristematic growth. Like calcium, boron moves with water through the soil and plant tissues, so its availability to plants is heavily dependent on moisture levels in the root zone, and it tends to be relatively immobile in plant tissues once it's been deposited. Another fun fact about boron is that dicots and broadleaf plants require significantly higher levels of boron than monocots. Next is manganese. Manganese is taken up actively by plants, meaning that the plant does not need to expend energy, or it does need to expend energy to pull manganese from the growing environment into the roots. Manganese is required for the hydrolysis of water and tends to accumulate at much higher rates in the margins of leaves compared to other plant tissues. Copper is also needed for electron transport during photosynthesis. In traditional soil production, copper is immobile and binds tightly with organic compounds. However, in hydroponic systems, copper availability is rarely an issue since there's no soil or organic compounds for that copper to bind to. Next is zinc. Zinc helps plants regulate water intake and use. Unlike most other nutrients, zinc's availability is inversely related to root zone pH, meaning it's typically more available at a slightly lower pH range. And finally, we have molybdenum. Molybdenum is absorbed passively through mass flow. This means that the plant does not need to expend energy to take molybdenum up and pull it into the roots and up into plant tissues. Molybdenum is needed in extremely low quantities, so molybdenum deficiency rarely occurs. Let's also take a quick look at chlorine or chloride. Chlorine is highly mobile in plant tissues and it's required by plants during photosynthesis. However, it's needed in such extremely low levels that the amount of chlorine found in most water sources is typically sufficient. Chloride toxicity and salt stress can occur very quickly, especially in water sources containing levels of chlorine over 70 parts per million. In recirculating hydroponic systems, chloride can accumulate very quickly, even when it's supplied by the water source at initially low levels. The more that solution recirculates, the higher the chloride builds. Next, let's discuss the differences between mobile and immobile nutrients. Many of you may remember this information from our webinar on macronutrients, but understanding which nutrients are mobile and immobile can go a long way towards identifying deficiency symptoms. Mobile nutrients can move through plant tissues. Once a nutrient has been deposited in the plant, it's able to be resolubilized and moved to where it's needed the most in the event of a deficiency. So typically plants will move mobile nutrients to actively growing sections. This is why mobile nutrient deficiencies appear first in older leaves, as those nutrients are removed and transferred to the younger tissues. Immobile nutrients, however, cannot be moved once they've been deposited in plant tissues. And when a deficiency occurs of an immobile nutrient, the plant will show symptoms in younger, more actively growing tissues first. Mobile nutrients include zinc, molybdenum, and chloride, and immobile nutrients are boron, copper, manganese, and iron. Next, let's talk about what a deficiency really is. A true deficiency is caused by a lack of nutrients and reduced plant uptake because of that lack of nutrients. Compared to toxicities, deficiencies are more common in CEA crops, especially longer-term crops like tomatoes and peppers. And a well-managed nutrient solution supplying all essential macro and micronutrients will rarely result in plants exhibiting deficiency symptoms. Generally, in hydroponics, it's more common for an excess of one or more nutrients to cause reduced uptake of other nutrients, rather than a true toxicity or deficiency caused by a total lack of one nutrient. Next, let's define nutrient toxicity. True nutrient toxicity is caused by an overwhelming excess of one particular nutrient. True toxicities are generally rare in CEA crops, as most crops are relatively short-term and recirculated solutions that are well managed will not accumulate nutrients to toxic levels. Now let's look at the specific deficiency and toxicity symptoms of each micronutrient. Iron is the most common micronutrient deficiency in CEA crops. Most of the time, iron deficiency is caused by improper root zone or solution pH, which causes the iron to be insoluble and not available for plant uptake. Because iron is immobile in plant tissues, deficiency symptoms typically appear in the younger tissues first, and this presents as a lime green, almost bleached appearance to those younger tissues. Iron toxicity is relatively rare in CEA crops, as iron can accumulate to high levels without causing plant stress. It's more likely that having an excess of iron would cause a manganese deficiency before resulting in a true iron toxicity. Next is boron. Boron is another common micronutrient deficiency, and it does have very distinct symptoms. It's usually very easy to identify. Because boron is immobile in plant tissues, those deficiency symptoms appear in younger tissues first, and those younger tissues will look stunted. The growth will be almost non-existent. It commonly causes a stubby appearance where the younger leaves stop growing and fail to develop altogether. Like calcium, because boron is linked to water movement through plant tissues, deficiencies may not be caused by a lack of available boron, but actually just low air movement and low transpiration, so the boron isn't able to be pulled through those plant tissues. Boron toxicity is uncommon, but it does present as leaf tip and marginal chlorosis. Extreme boron toxicity can cause necrosis of entire leaves. Manganese is also immobile in plant tissues, and like with iron and boron, those deficiencies present as generalized chlorosis, and they will appear in younger leaves first. Manganese toxicity is rare, but we did actually have an opportunity to identify a true manganese toxicity once in cannabis. The overall symptoms included chlorosis of lower leaves, misshapen leaves, and as you can see in this picture, a really distinct interveinal kind of streaking pattern. But in most cases, excess manganese will result in iron or molybdenum deficiency before progressing to a true toxicity. Next is copper. Under most growing conditions, even very low levels of copper will be sufficient and not cause deficiency symptoms. The sufficiency range for copper is very low, only about 3 to 7 parts per million for most crops. Copper is mobile in plant tissues, but it's very slowly mobile. It's one of those that's kind of in between. So it's more likely that deficiency symptoms will appear first in young tissues. Copper deficiency is so uncommon in CEA crops that unfortunately I couldn't identify a good picture example to show you today. However, copper toxicity is also rare. And excess copper will most likely result in iron deficiency and stunted root growth. So if you have the ability to kind of check out your roots and see that they're not really growing, they don't look healthy, I would, expect it to maybe be a copper toxicity. Next is zinc. Zinc deficiency results in shortened internode length, delayed maturity, and interveinal chlorosis. Zinc deficiency in plants can also be difficult to test for in crops that have been treated with fungicides. Many fungicide products contain zinc because zinc is really good at battling those funguses and pathogens that will attack your plants. So if you do suspect that you have a zinc deficiency, be sure to wash your plant tissues before submitting them to a lab for analysis, as those fungicide products will show higher levels of zinc than may actually be present in the plant tissues. And like with most micronutrients, zinc toxicity is rare, but an excess of zinc will most likely result in a deficiency of iron and manganese before it progresses to a true zinc toxicity. Finally, we have molybdenum. Molybdenum deficiency symptoms are very similar to nitrogen deficiency and cause general chlorosis and reduced growth. Molybdenum also has no consistent toxicity symptoms. It hasn't really been identified in any particular cases as an official molybdenum toxicity, and excess accumulation has shown very little effect in most plant species. So you can accumulate molybdenum to a fairly high level and not really expect to have any issues. Let's also quickly look at chlorine, because chlorine is needed at such low levels. Deficiency is incredibly rare. However, toxicity is more common and is generally associated with overall salt stress. On the left, you'll see a strawberry plant that was grown under a high EC and is showing the typical marginal necrosis we would expect from severe salt damage. Now let's move into section 2 and discuss how we supply and manage micronutrients in solutions. Micronutrients can be supplied to the nutrient solution through a couple of sources. The first, obviously, is through fertilizer. Most of our hydroponic formulas contain complete micronutrient packages, so you know that all the necessary nutrients are being supplied from the start. It's also really important when you're selecting a fertilizer to check the derived from statement in the guaranteed analysis. Always check to make sure that the micronutrients are supplied in chelated forms like EDTA, DTPA, and EDDHA to ensure that they'll be soluble across a broader pH range and stay plant available. And if you are having a micronutrient deficiency, we do offer a fertilizer blend that is just micronutrients. This is the label for our MOST formula. That stands for mix of soluble traces, and it can give your nutrient solution a much needed boost if you really struggle with low levels of micronutrients. Micronutrients can also be supplied by your water source. This is an example of a really hard water source that supplies a lot of calcium, but we also want to look at the micronutrients and be aware of what is in the water to make sure that we're not oversupplying those trace elements. This water source has a chloride level of about 65 parts per million, so we definitely want to be mindful of how that will accumulate in a recirculating solution over time. Plants aren't going to take up very much chloride, so as that solution recirculates, those levels are only going to get higher. Finally, we've gone over deficiencies. In the deficiencies section, how nutrient levels can impact uptake of other nutrients. This table highlights which excessive nutrients can cause deficiencies of other nutrients. I've bolded the micronutrients since we're talking about micronutrients today, but it is important to be mindful of all of the nutrient antagonisms. If you do suspect a deficiency or a toxicity of any particular nutrients, it's always best practice to have your nutrient solution tested before treating the issue. If certain nutrients are in excess, adding additional nutrients may not necessarily resolve the issue, and it could even complicate the issue further. So knowing the specifics of what is in your solution can help in making more intuitive nutrient decisions. For example, if your plants are struggling with a deficiency, is the best route to try and add more of a particular nutrient? Would it be more beneficial to adjust the pH? Or does the entire reservoir just need to be replaced with fresh solution and start from the beginning? This is where lab testing comes in, and it becomes a crucial step in nutrient management over time. We do offer a wide range of lab testing services, including water, nutrient solution, media, and tissue testing. So whatever your issue is, we can help get to the bottom of it and offer guidance on how best to treat the problem. So our key takeaways today are: one, micronutrients need to be supplied in the lowest quantities. They're supplied by several sources and can be supplemented using a micronutrient blend or even individual micronutrients. Micronutrient deficiencies can result from several factors, including overall low nutrient levels, imbalances of nutrients, or improper solution pH. And finally, lab testing is always the most accurate tool for diagnosing and avoiding nutritional disorders. EC and pH need to be monitored every day, but comprehensive nutrient analysis is essential for maintaining consistent crop health over time. And here's a link to our lab and lab testing services and my contact information if you have any additional questions. And at this time, I'll take any questions that you have. All right. Well, thank you all so much for joining us today. If you do have any additional questions, you have my contact information. Always feel free to reach out to us if we can help in any way. Have a good day.